We've looked at atoms in this unit. We've talked about electrons and protons and neutrons and all these little different pieces and how they fit together to make up all the atoms that we know about. But we haven't discussed how we know that there's pieces that make up atoms. And to get to that, there's actually a whole progression of experiments that were done in order to figure out all these little pieces of the atom. Okay, so starting all the way back with a guy named John Dalton, he presented the billiard ball model, which basically said atoms are it. There's nothing smaller than an atom. They make up all the different elements, and they lock together to make compounds. And then a guy named J.J. Thomson came along, and he said, well, that can't quite be right. We'll take a look at his experiment. He said, but there's got to be charged pieces in the atom. Based on what we've seen, there are charged pieces. And then there's also another experiment done a little bit later by Ernst Rutherford, and he found out, well, the charged pieces aren't really distributed evenly. There's a dense nucleus in the atom, and we've looked at Rutherford's model a little bit. And then this is the model that we tend to look at is electrons in energy levels because it's fairly straightforward. This was a guy named Niels Bohr, and he said, well, the electrons aren't just randomly in any space. They are in energy levels around the nucleus. And then we actually have the modern model, which says, yes, there's energy levels, but they're not rings. Rather, there's orbitals that are regions, three-dimensional regions of space where electrons are likely to be found. So let's take a look at how we moved from this model all the way up to the current modern model of the atom. So we got to start with Dalton. In John Dalton's model, he did a few experiments and he noticed that when he burned magnesium, it got heavier. And the reason it got heavier is it was reacting with oxygen. So he took magnesium, he burned it with oxygen, and he made magnesium oxide. And he figured out that the ratio of magnesium oxide to magnesium always occurred in the same ratio, which allowed him to say compounds form when two elements lock together, two or more. And they always do it in a fixed ratio. And not only that, he said, well, magnesium oxide has a different weight than anything else, and so he said, okay, so atoms of elements are unique. And we know atoms of elements are unique. We know that this is true and yet a little bit misleading at the same time. Atoms of an element are unique in that they all have their own number of protons, but remember, they can have different numbers of neutrons. Okay, so Dalton said, yes, elements are made of atoms. Atoms are as small as we can get. Compounds form when elements combine to make new substances, and they always combine in the same ratio. And this worked for a couple hundred years, really. Everybody started to experiment with this, and they said, yes, the atomic model explains lots of things about how compounds form and how elements behave. But then there was this guy came along named J.J. Thomson. J.J. Thomson was a chemist who actually spent some time working with a cathode ray tube, a Crookes tube, which actually is how the old TVs, the old big clunky ones that had the box in the back and then the curved glass front screen, they actually ran off cathode ray tubes. And basically what it was a stream of electrons that were excited and shot to the front of this tube and made the front of it light up, and you could see pictures on the front of the screen. Well, how do we make one ray light up the whole screen? Well, we do that because J.J. Thomson discovered we could do that. He said he actually did a lot of work with these cathode ray tubes. Let me show you a little video of this. This is an electron beam moving through a cathode ray tube. Thomson, when he first did this, didn't know this was an electron beam. What he has here is a tube that's mostly empty. It's a pretty high vacuum, so there's just a few particles of air in there, and it's hooked up to a power supply, pretty high voltage power supply. And when you turn it on, you get this beam of particles, this beam of light looking stuff that's moving from one side to the other, which isn't all that impressive. But then Thomson noticed that if you brought a charge plate up next to that beam, it would move either away from the charge or towards the charge, depending on if your charge was positive or negative. He noticed it moved away from negative charges and towards positive charge. And since people were aware of charge, they knew that an object could be positive or negatively charged, and like charges repel, opposite charges attract. That allowed Thomson to say, well, you know, that means there is actually charged particles within the atom. So because we had a tube of air particles, and air is neutral, so we had neutral particle, neutral particle, neutral particle, neutral particle, and then when you hook up electricity to it, these particles can transmit that electricity from one side to the other, and you can bend it around. He said, well, it's not good enough to say that this is neutral because it's got a charged particle in it. It's definitely got a negatively charged particle in it that we can move away from it. And that means there must be a positive charge in it too, in order to make this whole thing neutral. Now, what Thomson said, or his model, was actually the plum pudding model. And I've never had plum pudding in my life. I don't know what it's like. I imagine it's pudding with chunks of stuff in it. I like to call it the chocolate chip cookie model, where the cookie itself is positively charged, but the chocolate chips are negatively charged. So the whole thing is neutral, just like we think of atoms today, but the electrons and the are stuck to this neutral blob, which worked, but not for very long. So Thomson found the electron, and this started really ushering in some changes in how we think about atoms, because this model didn't hold up. And the reason it didn't hold up was because a guy named Ernst Rutherford did another experiment, and he did what's called the gold foil experiment, and I'll show you a little video on the gold foil experiment. So what Rutherford did was he took a radioactive source that shoots alpha particles, which are positively charged particles, and he shot them through a very, very thin layer of gold foil. Now, what he expected was that these alpha particles would mostly move straight through this gold foil. These alpha particles are fairly small. They're moving pretty quickly, and so he put up this film around them so that he could see where the radioactive particles were hitting, and then he had this gold foil in between. He expected most of them to move right through without much deflection. This gold foil was very, 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 very thin. Like we're talking 1 or 2 atoms thick. It was a very thin piece of foil. Okay. But when they actually did the experiment, when they played this through, they saw that some of these particles were actually bouncing almost directly backwards. It was like they were rebounding off of something. So while most of them did pass through without any deflection, some of them were deflected a little bit left and right, and some of them were deflected almost straight back. And this made Rutherford think, well, they've got to be running into something, but most of the space has got to be empty. And so if they're running into something and bouncing off of it, that something must be massive compared to them. And so this allowed him to say, well, most of the mass then must be concentrated in this center part, and it's deflecting these positively charged alpha particles. So the positive part is actually in the middle, and the negative part orbits it around the outside in the electron cloud. So this is Rutherford's model of the atom. It puts the positive nucleus in the middle, and it puts electrons around the outside. Now, Rutherford actually did not find the neutrons. He found the protons, and he found the nucleus. He didn't know about the neutrons. Another scientist by the name of Chadwick found the neutrons. We're not going to get into his experiment. But this basically brings us up to getting close to the modern atom. So we have electrons outside the nucleus, and the nucleus is positive. Okay, we got to take it one step further, and that's what Niels Bohr did. Okay, so Niels Bohr was a scientist, and he was aware of the nuclear theory of atoms. He knew there was a nucleus in there, but what he was looking at was how the electrons are arranged. And he noticed in his experiment that you can take, say, hydrogen gas, and if you put a little bit of hydrogen gas in a tube, and you send current through it, it acts like a light bulb, except that it doesn't produce white light. It only produces a certain color of light. So the whole spectrum of light runs from red all the way to violet, right? Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And he noticed that the hydrogen was only producing a certain color or two, couple lines of color when he did this. And he noticed some different elements would do different things, produce different colors. Well, about this time we were also figuring out, or scientists were also figuring out, that colors of light are related to how much energy is present. And so red actually has low energy, violet has high energy, and everything in between is in between. And so he was able to say, well, because these electrons are, or because this atom is always producing that same color light, it's always producing light with the same energy. Wavelength is related to energy. We'll get into this much later in the year, but that allowed Bohr to say, well, it must be that these electrons can only emit certain amounts of energy because they can only emit certain colors. And indeed, it turns out that the nucleus in the middle, positively charged, surrounded by these electrons in energy levels. Okay, when an electron gains energy, it can move up an energy level or 2 or 3 energy levels. But when it doesn't like to be up there, right? Because this is positive and these electrons are negative, they're attracted to that positive nucleus, so they fall back down. But energy can't be created or destroyed, so it has to get rid of some energy, and it gets rid of that energy as light. Okay, so light is a form of energy, and it's emitted by electrons as they fall to lower energy levels. And if it falls 1 energy level, it might emit green light. If it falls 2 energy levels, it might emit violet light, but it doesn't emit any other color lights because it only has these discrete bands it can fit into. And so this is what Bohr observed, and so he was able to say, well, electrons aren't just randomly orbiting, they are only found in energy levels. They can move between energy levels, but they're never halfway. They don't occupy these regions between energy levels. And this model works pretty well, and this is the model we stick with, although if you take a little bit more chemistry, you'll learn about this model of the atom where it says there's actually orbitals and regions of space where these electrons are likely to be found. We won't get into that one, we'll stop here, but it is true that electrons move in orbitals, and these orbitals occupy energy levels. So we didn't eliminate energy levels, we just added one more layer to it.